right, and we live. Good morning, kiddos, or afternoon, depending on what time of day it is or what class period I have. Today we're going to do lesson 13. In lesson 13, we're working with applications with numbers in scientific notation. To give you the gist of it right quick, we're basically just going to be, multiplying, dividing, and whatnot, just working with various operations in scientific notation. Just a quick recap, I do suggest and highly encourage that you look back at lesson 11 and lesson 12 in case you need a quick reminder of what we were doing before I got sick. In lesson 11, we were putting numbers in scientific notation, but it was very small numbers. We were working with decimal numbers and putting it in scientific notation properly. In lesson 12, that's where we were doing the properties of exponents. So that's the products of a product and products of a quotient and so on and so forth. Basically what we put in that table on page 81 and what I have on the wall, that's what we were doing for lesson 12. Today in lesson 13, we're just going to apply it a little bit. Nothing too drastic, nothing too long. Today's lesson should be fairly quick. So we're going to make this smooth sailing. First, we have our warm-up as usual. I'm going to read the instructions right quick. Write each expression in scientific notation. As you can see, you have a number given to you in scientific notation with an exponent on the outside of the parentheses. As we were doing before I left, you're going to apply that outside exponent to the quotient, the coefficient and the exponent on the inside. So you're going to multiply that outside exponent to the inside. So you're going to, I did number one for you. We're going to multiply 2 times 3, those two exponents there. And obviously 2 times 3 is 6. And then we're going to apply that squared power to the whole 3 at the front, our A value. Every number, let me not forget to write this in. And let me make my thickness a little bit higher so maybe y'all can see it a little better. But every number has an invisible 1 over it. Don't forget that. Okay? That's our invisible exponent, and we're going to multiply it there. 2 times 1 is obviously 2. 3 raised to the power of 2 is the same thing as saying 3 times 3. 3 times 3 is 9. That gives us the answer of 9 times 10 to the 6th power. I'm going to give you some time to do number 2, 3, 4, 5, and 6. I'm going to give you maybe 5 minutes to work on that silently, so pause it here to allow work time. And we're back from warm up, getting into our lesson for today. We're going to skip past this just a little bit. It's not much. It's just a video of stacking planets to compare the size. As you can see, as you move through the solar system, the planets get larger and larger. So there's a bit of a comparison there to be made about how much larger or smaller are certain planets compared to other ones. And then likely that answer would be in scientific notation. So that's the gist of what this was, but we're not going to waste time. We're going to skip right past that. In our lesson first, operating with numbers in scientific notations, you can see we have a little balloon here. That's what's in the blue. The yellow is the preferred size of the balloon that we might be trying to get to in this particular example. And then we have a hypothetical breath count of 100. So you might have to breathe into the balloon 100 times to blow it up all the way, hypothetically speaking. For number 1, make sure you write this down, because from my understanding, all of your notes today, yet again, you're going to have to write them yourself. There's nothing pre-written for you, so take really good notes, from my understanding. For number 1, I'm going to just read it off. On average, an 8th grader's lungs can hold about 3.6 times 10 to the negative 3rd power cubic meters of air per breath. Underline that. Okay? That's giving us some context clues. We have 2 questions here. For A, what volume of air is in 2 breaths? Write your answer in scientific notation. What volume of air is in 2 breaths is basically asking us to multiply it by 2. Or you can add 3.6 times 10 to the negative third to itself 2 times, but I think multiplying is just a little bit quicker. So that's how we're going to work it out. And I'm just going to write this here, write what I'm writing. Do not leave anything blank. Some of y'all have a bad habit of that. And then when it comes time to study, you don't know what's going on. So we're just multiplying this by 2. Just off the top of my head, excuse me, goodness. Just off the top of my head, I know that 3.6 times 2 is going to give me, I'm sorry, my phone's going off. Give me 1 second. 3.6 times 2 is going to give me 7.2. Okay? Times 10. Once again, we're going to I'm sorry, hold on. I'm just verifying here. Making sure I got my math straight. We're going to multiply that 10 to the negative third by 2. That'll give us 10 to the negative 6. 10 to the negative 6. And I'm just verifying here my calculator. Just to make sure. I know you cannot see because I happen to be using the calculator on my phone. So I apologize that you can't see what I'm doing. Okay. I take back a small piece of information. I tricked you guys. I hope that you caught it. Take a pause, and what did I say wrong? If you're back now, you would know that if I'm going to multiply something by 2, that I do not have to multiply the whole number 2 by the power that it is raised by. That's the trick that I gave you. Do not fall for that. Okay? If we're going to multiply this whole number 2, we only need to apply it really to the a value. You don't have to apply it to the n value, which is the exponent, unless that 2 is a raised power outside of the parentheses. So we're going to keep 10 to that negative 3 the same. Okay? Keep that the same. That's all we need to do. Don't fall for that. For B, B says what volume of air is in 10 breaths. So if you breathe 10 times, what answer will you get? Make sure you write your answer in scientific notation. Pause here to allow work time. If you're back, we're moving on. Here, same type of example. We're still working with this balloon. And we have a goal of 3.6 times 10 to the power of 0 cubic meters. Real quick, what is any number raised to the power of 0? If you're back, then you've answered that any number raised to the power of 0 is 1. Therefore, 3.6 times 1 cubic meters, we're just trying to blow this balloon up to 3.6 cubic meters. That's it. For number 2. Number 2, the volume of each breath is about 3.6 times 10 to the negative third cubic meters. Underline that. How many breaths, underline that, does it take to reach the goal of filling the balloon with 3.6 times 10 to the 1 cubic meters of air. Underline this number, that 3.6 cubic meters of air. That is hypothetically assuming it's already blown up with air. And if the volume of each breath is 3.6 times 10 to the negative third, and we need to know how many of something. Remember when I said if you are given a phrase and it's asking you how many of something, typically you're going to divide. Make sure you annotate that above. Dividing. Okay? And this number here is the bigger number. Do not get fooled by that power of 0. 0 is higher or more than any negative number you can have. Okay? So 3.6 times 10 to the 0 is bigger than 3.6 times 10 to the negative 3. So that's how we're going to set it up. And I'm going to keep it in scientific notation just because that's how we need to write our answer. Setting up division equals. First, you're going to just divide your A values. By chance, they are proportional. 3.6 divided by 3.6 is 1. Any number divided by itself is 1. And then we're going to divide 10 to the 0 by 10 to the negative 3. If you can remember, we did this before a couple of lessons ago. And if I'm going to divide with like basis, dividing with like basis, then all we need to do is subtract our exponents. Okay? We have a double negative here. We can't have that. Double negatives always result in either positives and or addition. So that'll give us 10 to the 0 plus 3. Then that gives us 10 to the 3. Okay? And we're just going to pop that up here. So to answer the question, it will take 1 times 10 to the 3 breaths to reach the goal of filling the balloon with 3.6 times 10 to the 0 cubic meters of air is how you will properly answer that question. Take a few seconds to write that down. Yes, you need the whole sentence. Before we move on, take note of that 1 times 10 to the 3. If we take it out of scientific notation and put it back into standard form, that'll give us the number 1,000. Just annotate that somewhere on your paper. Moving along. For number 3, complete the comparison statement. That's what we just did for number 2. This is just another sentence. Okay? The volume of the goal is, that's this number, 3.6 times 10 to the 0. You'll put that in that first blank. Okay? 3.6 times 10 to 0. 0 cubic meters. That is, and you don't have to write the whole scientific notation here. You can just put 1,000 if you want to, because that's what I'm going to do. But if you want to be consistent and just put 1 times 10 to the 3rd, that's fine. That is 1,000 times as much as the volume of a single breath, which is, and I'm going to just scroll down a little bit so we can see. That was 3.6 times 10 to the negative 3. Fill that in. While you fill that in, I'm just going to read off number 4. On average, an 8th grader breathes 14 times per minute. Underline that. Assume you've been breathing up at about the same rate your whole life. Okay? Number A. A is a hypothetical situation. About how many breaths have you taken so far in your life? Just take a guess. Just take a guess and write your answer in scientific notation. Pause here to allow work time. If you're back and you have your answer in scientific notation, we're moving on to B. If the volume of one breath that you take is the same as the volume from the last example, 3.6 times 10 to the negative third cubic meters, then what is the approximate, underline that, so we're going to round, what's the approximate total volume of breaths you have taken so far in your life? Keep your answer in scientific notation. So here for B, all you're going to do, like how we divided for number 2, you're going to divide it here for B as well, except for you're going to use the amount of breaths that you're taking so far in your life, written in scientific notation. And we're going to divide that by the 3.6 times 10 to the negative third. This is just a little bit of practice. Pause here for work time. If you're back, we're moving on. New example. In this example, we have the moon up here at the top. I don't know if you can see it, so I'm just going to underline it a little bit. That's the moon there. We also have the earth here. And then we got some money. Something everybody wants. So we're going to be doing a comparison here. For number 5, $1 bill is 0.11 meters thick. Underline that. Annotations, kiddos. Annotations, don't forget about them. About how many dollar bills will it take to make a stack 1 meter tall? So we need to know about how many dollar bills. So that means we can round. And we have how many again, so that means we're going to be dividing again. Divide. And we're trying to get to a stack that is 1 meter tall. And write your answer in scientific notation. Now, real quick, if we're going to go from millimeters to meters, we're going to have to convert a little bit first. I have that conversion pulled up right here. 1 millimeter is 0.001 meters. Okay? 1 millimeter. 1 millimeter is 0.001 meters. If I turn this conversion around, because I can see that I have 1, 2, 3 decimal places. If I work backwards, then that'll also tell me that 1,000 meters will give me 1 millimeter. And just to show you, I'm going to put that in Google backwards for you. So 1 meter is 1,000 millimeters. I'm sorry, did I say 1,000 meters? Excuse me, I think I said that backwards. Sorry. I think I might have said that backwards. 1 meter is 1,000 millimeters. Is what I meant to say. And I'm just writing that conversion right here. Okay? Now, a dollar bill is 0.11 millimeters thick. First of all, we need to convert that to meters. So we have 0.11 millimeters. We're going to put that over 1. To get to meters, meters on top, millimeters on bottom, so we can cancel out. We're just going to put that conversion here. You should have learned how to do this back in 7th grade, conversions. If I convert a little bit and I do 0.11 divided by 1,000, that will give me 0.00011. In scientific notation, I know that my A value is going to be 1.1 because those are the only two numbers we can work with here because we can't have zeros in the A place. And me just counting off my hops, I did 4 hops to the right. Okay? But I also did it with a small decimal number, like how we did in lesson 11. So that 4 is going to be negative. All right? Take a pause here so you can write that down. So we have 1.1 times 10 to the 4. I'm just going to erase a little bit, or at least try to. And then I'm going to give you some time to solve number 5 on your own. I am going to help you to set it up. Matter of fact, let me just draw in a different color just in case. I'm going to go back to that red. So we've converted the measurement of dollar bills to meters. We still need to know how many dollar bills will it take to get to 1 meter tall. So we're going to take that 1 meter and divide it by 1.1 times 10 to the negative 4. Pause here to allow work time. Solve as a class before we move on. If you're back now and you've done your division correctly, you should have the answer of 1.1 times 10 to the positive 4. That's how many dollar bills you need. Moving along. Our last couple of questions, and you will do these independently, but we will check together. I'm just going to read them off right quick. The moon is approximately 3.84 times 10 to the 8 meters away from Earth. $1 bill is 0.11 millimeters thick. About how many dollar bills will it take to make a stack from Earth to moon? Write your answer in scientific notation. Just to give you a hint, you're going to need that dollar bill conversion that we just did, this 1.1 times 10 to the negative 4. You're going to need that to divide for number 6. In number 7, in February 2019, the U.S. national debt was about $22 trillion, or 2.2 times 10 to the power of $13 in scientific notation. Make a comparison statement. That means you're going to write a sentence between the value of the Earth to Moon stack of dollar bills in problem 6 and the national debt. So all that means is you're going to take your answer from number 6 about on how many dollar bills you need, and you're going to compare that to the U.S. debt. So you might say, if you divide that, it'll take $1 billion, hypothetically speaking, from number 6 to reach the $22 trillion debt in number 7. So you're just going to make a little bit of comparison. Just do a little bit of math. Or you can say that the amount of dollar bills from number 6 is maybe 10 million times more if we're going to multiply than the $22 trillion debt. So you have a little bit of free range here to set up this comparison however you want to. Just make sure it makes logical sense and make sure that your numbers are as accurate as you can get them. Okay? Take a pause to allow a little bit of work time. if you're back. We're moving on. We're basically at the end. Quick question. What tools or strategies can help you solve problems in context that use numbers written in scientific notation? We're going to skip number 2. What did you find interesting about today's lesson? If anything, but personally I didn't, so I'm just going to skip right on past that. Your exit ticket. Your exit ticket is one question, but I'm giving you 2 points. You're going to earn 1 point for showing your work. So yes, you have to show your work. Don't just give me an answer. You're going to earn a 2nd point based on your sentence that you give me. So solve it and then answer the question. That is 1 point each. It's 2 points. I will give you a tip though. You're going to have to divide. So just be ready to do that. Okay? In the practice section. So we're going to skip past the recap because we don't need it yet, unless you need it just to have a reference. In the practice section, circle number 1. I want you to do number 1, the whole thing, part A and part B. Turn the page. Circle B and C from number 2. Okay? B and C. From number 3, circle B and C as well. Okay? I know this is your practice section, but you will not have practice work. This is your homework. If we have time in class, knock it out now. All right, get a head start. This is where you ask questions if you have any. Your extra credit, as usual, is the remember section, and it's up to you if you do that part or not.